good afternoon, and good morning. So in the previous videos, we have actually discussed on differentiation, right, for trigonometric functions, right? So we've talked about the basic trigonometric functions: cosine of x, sine of x, and the tangent of x. We've also talked on how to differentiate the reciprocals as well, like secant of x, cosec of x, right, as well as cotangent of x. And we've also talked about their inverses, right? So cosine inverse of x, sine inverse of x, and tan inverse of x. Okay, so this is what we've discussed from the previous video, right, on these sets of functions. And now for today, we're actually going to talk about exponential functions, how to differentiate exponential functions, natural log, right, so the ln of x, as well as the log, which is to the base of 10x, right? And we're also going to talk about the hyperbolic functions, right, such as sine hyperbolic x, cosine hyperbolic x, and a tangent hyperbolic x, as well as the inverses. So it would be sine inverse hyperbolic x. That's what I mean to say. It's supposed to be, my bad, yeah. Okay. Right. Then of course the cos hyperbolic inverse of x, and then the tan hyperbolic to the inverse of x, and also be talking about their reciprocals. So cosec hyperbolic x, sec hyperbolic x, and cot hyperbolic x. So this will basically be the focus for today's tutorial session. So the focus, right? So therefore, yeah, we're gonna look into that as well as some problems. Okay, so let's start with the exponential functions, right? So when you differentiate an exponential function, okay, and you find its derivative, we end up having the exponential function, okay? And when we are differentiating the natural log function, okay, we take the derivative of it and we'll end up having just 1 over x, okay? For the log base 10, okay, if we take the derivative of it, what happens is that we tend to get 1 over x multiplied by log base 10 e, okay? So that is for the case when we're dealing with exponents and logarithmic functions. It's fairly straightforward, fairly easy to remember, but again, most of the time in the exams they'll actually give this formulas to you, right, in case if you don't remember. But again, these are quite simple, so it's quite easy to actually remember these functions, especially for the exponential and the natural logarithm. And the log to the base 10 is just it's just like the ln function, except you just have this log to the base 10e. That's it, you just multiply it. So that's about it. All right, so then now we're gonna talk about the hyperbolic functions, right, and the inverses as well. Okay, so for hyperbolic functions, okay, if we are dealing with sine hyperbolic of x and you want to find the derivative of it, it's actually cosine hyperbolic of x, or you can write it like this: it's just half e to the power of x plus e to the power of negative x. So there's actually two ways to express the derivative of the hyperbolic sign, right? It can either be in cosine hyperbolic x, and also half times e to the power of x plus e to the power of negative x. Okay, for cosine of hyperbolic x, okay, if we take the derivative of cosine of hyperbolic x, right, is just sine hyperbolic x, okay, or you can write it like this. It is 1 over 2 e to the power of x minus e to the power of negative x. Okay, so just like the sine hyperbolic function, if you were to differentiate the cos hyperbolic x, you'll end up having sine hyperbolic x, or half times e to the power of x minus e to the power of negative x. Okay, and then for the tangent, the tan hyperbolic, if you were to differentiate it and find its derivative, it would actually be sec hyperbolic squared x. Okay, so it become the second hyperbolic squared, the second hyperbolic x squared. Okay, so that's for tangent hyperbolic x. So these are for the basic three functions, and just to clarify that there is no alternative for tan hyperbolic x. When you do the derivative, you only have sec hyperbolic x squared. Okay, now let's move on to the inverses. Okay, I think, yeah, I'll erase them right away. Okay, so for the inverses, if we are trying to find the derivative of sine hyperbolic inverse of x, the derivative would have been 1 over square root 1 plus x squared. Okay, if we're taking the derivative of the cosine hyperbolic inverse of x, if we take the derivative of it, we'll end up having 1 over square root x squared minus 1. Okay, and of course we have to make sure that x is obviously greater than 1, right, for it to happen. And for tan hyperbolic inverse, okay, or ddx, okay, it is quite simply 1 over 1 minus x squared, where the modulus of x has to be less than 1, and as we've explained that before, what it means is, it means to say that x is between -1 and 1. Okay, so that's for the inverse hyperbolic. Alright, and yeah, I think that's pretty much about it for the inverse hyperbolic. Okay, and the last but not the least is gonna be the reciprocal. Okay, so we're gonna talk about the reciprocal actually. So let me erase this real quick. So for the reciprocal, okay, so cosec hyperbolic x, if you find the derivative of it, it would be equal to negative cosec hyperbolic x multiply with cot hyperbolic x. Okay, for second hyperbolic x, if we take the derivative of it, okay, it would be negative second hyperbolic x times tan hyperbolic x, and last is the cot hyperbolic x. If we take the derivative of it, we'll end up having negative cosec hyperbolic x squared, right? So basically we're going to the square of the negative cosec hyperbolic function. All right, so yeah, that's pretty much it for cosec hyperbolic x, sec hyperbolic x, and cot hyperbolic x. So yeah, so these are basically the derivatives for all the hyperbolic functions, exponent functions that we as well, and the inverse that we've listed earlier. So let's proceed with solving some problems. And for hyperbolic functions and exponent functions as well as logarithmic functions, usually they would give the derivatives to you, okay? But in the case if they don't, then it's best to probably memorize it actually. In most cases, they would tend to give it to you actually, derivatives, so you don't really have to memorize it. So let's do some questions, right? Let's see what we have here. So the first question actually says that differentiate, okay, differentiate this function, okay, fx is equals to e to the power of x over 1 plus e to the power of x. Okay, so once again, just like always, please do pause the video and give this question a try, so that later when I go through the answers, it'd be much helpful. Okay, so assuming that you guys already paused and give it a try, the first thing we can do to solve this problem is, obviously this is fx in the form of e to the power x over 1 plus e to the power of x. So it's basically, we use the quotient rule. I'm going to denote this as u, I'm going to denote this as v. So we know that u is equals to e to the power of x, and if we differentiate u with respect to x, so du dx, and take the derivative, is just simply e to the power of x. Whereas for v is just simply 1 plus e to the power of x, and if we take the derivative of v with respect to x, we'll also end up with ex. And we know from quotient rule that we've learned a few videos ago that f prime of x is equals to v du over dx minus u dv over dx over v squared. So frankly, it is just 1 plus e to the power of x times du dx is e to the power of x minus e to the power of x, u dv dx will of course be e to the power of x, okay, over v squared. So v would be 1 plus e to the power of x squared, okay. And if you want to simplify it, we'll end up having e to the power of x plus e to the power of 2x minus e to the power of 2x over 1 plus e to the power of x squared, leaving us with e to the power of x over 1 plus e to the power of x squared. Okay, so that's basically the derivative of the first function. So it wasn't, that bad, because honestly, you've learned the quotient rule, and differentiating e to the power of x is really a joy, because it's not as complicated. So let's go to something a little bit more different, a bit more interesting. Right, so I'm gonna erase this real quick. Okay, right, so let me write down the next question. So we're differentiating fx is equals to ln, right? So we have here 2x plus 1 over 1 minus 3x. Okay, so again, please do pause on the question and give it a try. Alright, so I'll give you some time to pause this video and give it a try. Okay, so assuming that you guys have paused this video and give it a try, so let's try to write the function first. So fx is just ln, okay, of 2x plus 1 over 1 minus 3x. So we can see that the ln is the outermost function, right? Okay, that's the outermost function, and this here is gonna be our second function, the innermost function. So this is basically, we have to use the chain rule. Okay, in this case I was thinking of actually using the faster variant of it, the out and in rule that we have learned earlier, but sorry, out and in, oh my god, okay. But the thing is, we actually have a reciprocal, right? We actually have a fraction, not reciprocal, sorry. We have a fraction of two functions, okay, which is in the form of fx over gx, and the only way to differentiate this, okay, to get f prime, sorry, not f prime x, to get the derivative of this, right, in order to get a derivative of this function, which is obviously you want to find the d dx of fx over gx, we need to obviously use the quotient rule. Okay, so this will take a bit of time, and in this case we have to substitute this fractional, well, this function, right, that's in terms of fx over gx, into a much more differentiable function, right? So in this case I'm gonna take this as u, okay, I'm gonna call this u. So u equals to 2x plus 1 over 1 minus 3x, and of course I'm going to express fx as fx equals to ln u. So dfx over du is just simply 1 over u. That's pretty straightforward. And for u, if you want to differentiate it, you'll of course have to use the quotient rule. So this will be our u. Okay, let's not use u actually. We already used u twice. So let's use a different letter because we've already used u before. So let's just call it as b, and let's call it as v. Right? So b is obviously 2x plus 1. So db over dx is equals to 2. V is equals to 1 minus 3x. Therefore dv over dx is equals to negative 3. So if we of course do the product rule, right, to find du dx, du over dx is just simply v db over dx minus b dv over dx, right, over v squared. Okay, so as you try to solve it, v is obviously 1 minus 3x, dv dx is 2, so it's just simply 2 1 minus 3x. Okay, 1 minus 3x, and it's gonna be minusing with b. B in this case is 2x plus 1. dv dx is negative 3, so negative negative become positive. So 3 plus 3, 2x plus 1, okay, over v squared. So in this case our v squared would be 1 minus 3x squared. Okay, so with that being said, actually let me just erase this first. Okay, I want to clear some space. Okay, so yeah, I want to simplify du dx actually, so let me just simplify it here. So du dx would be equivalent to what? It would be 2 minus 6x, right, plus 6x plus 3 over 1 minus 3x squared. So 6x and minus 6x will cancel, leaving us with 5 over 1 minus 3x squared. Okay, so we're going to erase this as well. Okay, so oh, sorry, I didn't mean to erase the u actually. Let me just rewrite that again. So u is obviously 2x plus 1 over 1 minus 3x, and we've got the derivative. So therefore, using the chain rule, so dfx over dx is equals to dfx over du times du over dx. So dfx over du is 1 over u, so 1 over u actually would be 1 minus 3x over 2x plus 1 multiplied with, okay, so multiply with 5 over 1 minus 3x squared. And of course we can simplify this further because, well, if we cancel this too, we'll just be left with 1 minus 3x, right? So therefore your final answer would be 5 over 2x plus 1 times 1 minus 3x. Okay, so this will be the final answer actually after you differentiate it. So this was a bit, I would say, a bit tedious. I mean, because we have a bit of steps, right? We had to obviously use chain rule, right? Differentiate the logarithm followed by this particular function that we labeled as u. Alright, we've labeled it right here, and then of course we had to use quotient rule, and eventually we came up with our answer for du dx. And yeah, so as I've said in the previous videos, usually differentiation, especially of complex functions, may include like 2 or 3 rules in one question, so just be aware of that. Okay, so moving on, let's go for an interesting question. Okay, so let's differentiate the function fx given to us. It's just simply cosine of x times the cosine of hyperbolic x. Okay, so again, I'll give you guys some time to actually you know, pause and solve the problem, right? So yeah. Okay, so assuming that you guys actually, you know, given your time to solve the problem, let's just try to write the function down. So it's just simply cosine of x times the cosine hyperbolic of x. Okay, and clearly we have to use the product rule here, right? Because it's the product of two functions, u and v. Okay, and we know that u is cosine of x, and du over dx is negative sine of x, whereas for v it is cosine hyperbolic of x. Then dv dx would be actually in this case it would be sine hyperbolic x. Okay, so we will just leave it as sine hyperbolic x. So we know that from product rule, okay, so fx is equals to what? It's just v du over dx plus u dv over dx. So it would be cosine hyperbolic x times negative sine x plus cosine of x times sine hyperbolic x. So we can just leave it like this. So it becomes sine x plus times cosine hyperbolic x plus cosine x plus sine hyperbolic x. Okay, so yeah, that's basically it. Again, a fairly straightforward problem, right? and yeah, it's not too bad. Let's go for another one. Okay, let me erase this real quick. Let me erase a little bit bigger actually. Right, done. Okay, so let's go for another question. Let's see what we have here. Okay, so a function root 1 plus x squared. Okay, square root multiplied with the inverse of sine hyperbolic x. Okay, so again, I will, give you guys some time to pause this video and give it a try. All right, and yeah. Okay, so assuming that you guys already paused this video and try to try out this problem, let's solve it together. So we have fx in the form of 1 plus x squared root, right, and sine hyperbolic inverse of x. And actually what we can do is, remember, we can write this root into a form of 1 plus x squared to the power of half. Okay, so that's the idea what we're doing here. And this is also just as similar as the previous problem. You have to use product rule, right? Two functions, so u and v. So we know that u is obviously 1 plus x squared to the power of half, and du dx. So we're gonna use a bit of in and out here, out and in, right? Because we see the power is first, right? The power is the outermost, right? And then of course followed by the innermost function, which is just 1 plus x squared. So we're gonna of course consider the power first, so it'd be half. Oh, sorry, I'm using yellow, so we're using blue, by the way. Okay, so it would be this case, it would be half, okay, 1 plus x squared to the power of negative half, right, multiplied by 2x, leaving us with x 1 plus x squared to the power of negative half. And then for v, we know it's sine hyperbolic inverse, right? And then dv dx is 1 over square root 1 plus x squared. Okay, so it becomes square root 1 plus x squared. Okay, so as we know, for product rule, f prime x is just equals to v du dx plus u dv dx. So it would be sine hyperbolic inverse multiplied with du dx. So it's just multiplied with x, okay, over square root 1 plus x squared plus u, which is just square root 1 plus x squared, and dv dx is just 1 over that. Okay, so just 1 plus x squared root. So you can simplify this problem into 1 plus x squared, right, plus x sine hyperbolic x over square root 1 plus x squared. So yeah, this is basically your derivative, okay, for this function. Not too bad, just involves a bit of product rule and yeah, the inverse hyperbolic function. Now I think there is just one thing that I didn't really consider in the question, and that would probably be the log to the base 10. Okay, and Apparently I tried looking for the textbook to see if there was any question specifically asking about log to the base 10, and there's none. So we're gonna make our own question on the spot and yeah, try to solve it. Okay, let's see. So it would be in this case, let's try out log let's see, cosine hyperbolic inverse x over let's see here what we can do here, e to the power of x plus ln x. Okay, so this will be a bit of an interesting question actually, right? Again, I do advise you guys to pause this video and try to find the derivative for this function right here. Okay, and yeah, we'll get back onto it. Okay, so I assume that you guys already paused and give this video a try, and I mean this is a question a try. So of course we have here fx is equals to the logarithm, okay, of the cosine hyperbolic x over e to the power of x plus ln x. So this one actually, what you're gonna do is obviously, you know, use the chain rule, right? So I'm gonna take this as u, okay? So we know that fx can be expressed as the logarithm of u, okay? And we know that dfx over the derivative of u is just 1 over u times the logarithm of e, okay? Or base 10 of e, okay? That's pretty straightforward. Now, for the second part right here, which is, I'm gonna have to write down by the way, it's gonna use a white color, is that u is equals to cosine hyperbolic inverse of x over e to the power of x plus ln x. So I'm gonna have to use quotient rule for this. So this will be my u, this will be my v. Actually not u, let's not use u, it'll be really confusing, right? Let's use a different letter, let's use b. Okay, so in that case we know that b is cosine hyperbolic inverse x, then db dx would be, in this case, 1 over square root x squared minus 1. Okay, and v is e to the power of x plus ln x, and dv dx would be e to the power of x plus 1 over x. Okay, so now if you want to find du over dx, is just, as we know, is just v, turn out to u. I keep on switching it to du automatically. Actually it's not really du because we're now using it in terms of b, but the rule is still the same, yeah? So it would be v db over dx minus b dv over dx over v squared. Okay, so if we plug and play it, oh, it's going to be quite a big function by the way. It's going to be e to the power of x plus ln x, okay, over square root x squared minus 1 minus, and I can't have space here unfortunately. Let's see, so I'm going to have to erase this part by the way, yeah, just to create some space, but we already know what quotient rule is, so I don't think that should be a problem. So in this case it will be just e to the power of x plus ln x over square root x squared minus 1 minus cosine hyperbolic inverse of x, and we have e to the power of x plus 1 over x, okay, and it's over e to the power of x plus ln x. Okay, so that's our du dx. Then of course we'll have to use the chain rule. So I know it's gonna be a bit messy, right? Because we're dealing with multiple functions. So we know that dfx over dx is clearly dfx over du times du over dx, right? So that's the chain rule, and I'm gonna have to erase that because we need some space. So that would be 1 over u. So it would be e to the power of x plus ln x over cosine hyperbolic inverse, right? Cosine hyperbolic inverse x times the log e, obviously, log to the base e, multiplied with this very bizarrely long function. So just e to the power of x plus ln x. Okay, I do apologize for the messiness in the writing. X squared minus 1 minus cosine hyperbolic inverse x ex plus 1 over x, okay, over e to the power of x plus ln x squared. And yeah, I think I forgot to do it in the previous derivative. Yeah, squared. Okay, so I think we can see that, I don't know if you guys can notice actually, by the way, that this and this we can factor out, right? Eventually we leave it as e to the power of x plus ln x, okay? And yeah, basically you can simplify it, so you'll just be log e over cosine hyperbolic x inverse multiplied with this mumbo jumbo looking expression right here. But yeah, that's basically how do you find df dx for this case, okay? And it's not hard, it's just that sometimes in the exam, or maybe in the midterm or the mid test, whatever you guys have, or in your quiz, they might end up giving something a little bit more tedious or complicated, right? But as long as you know what steps you need to do, in this case our steps were only 2, which we had to obviously do the chain rule, okay, and the quotient rule, okay, and if you know the right derivatives, you can easily solve these kind of problems and end up getting the answer actually much easily, right? So that's basically the whole idea for all the differentiation videos that I've been actually posting, including today's one, right? This video right here. And yeah, that will be actually all for today's video. So for the next video, we'll be looking more towards into two different things. We'll be looking into parametric functions, right? How to differentiate parametric, and also for implicit. All right, so we're going to do for parametric and implicit functions. All right, and of course later we'll go talk about optimization, right, using derivatives. So that will be for the next few videos, okay? So this is like for future videos, okay, future videos which will be coming soon. So yeah, again, thank you for watching this video. Alright, so thank you so much for watching today's video, and hopefully that will be all.